So yesterday we talked about calorimetry, which is heat transfer from one object to another. Today we're going to go more in depth with that heat transfer, and we're going to talk about what happens when heat transfers from something to another thing and a phase change occurs, or we see those temperature changes over a long range of phases. It's called a heating curve or a cooling curve. And if we look at this heating curve, we have whatever our object is starting at some temperature T initial. And go ahead and draw this graph. You need this graph in your notes. At T initial, it is a solid. So we have a solid object. And we start adding energy to it over time. And as we add energy to a solid, we found out yesterday that the temperature changes. And this whole time, the temperature is changing as energy is added. We're going to call this section 1. In section 1, we can do Q equals mc delta T to calculate the amount of energy added. Our heat equation, as long as temperature is changing, we have C for the solid, whatever that is, the mass and the temperature change for section 1. So solid, 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 solid. At some point, the solid reaches a temperature where it starts to turn to liquid. What's that called? Melting. We've reached the melting point. And at the melting point, which is right here, I'm going to call that T melting, we get a flat line on our graph. There's energy being added, but the temperature is not changing. So there's no slope. Section 2 of the graph, I can't use Q equals mc delta T. If I plug in a 0 temperature change here, I'll wind up with 0 energy. But it's obvious from the graph that energy was being added. That's because all of the energy being added is not going into changing the temperature. It's going into overcoming those intermolecular forces and pulling the solid particles farther apart to make them a liquid, making them move more freely. For this part, to calculate Q, we use something called the enthalpy of fusion times the number of moles. And this delta H, let's make a note of this somewhere else, is called enthalpy. We'll talk more about that tomorrow. But it's energy added per mole of substance, joules per mole. This is a special enthalpy. The enthalpy of fusion, fusion is a fancy word for melting. You only use this when something's melting. And it's the energy added per mole. All right? As the line is flat, I'm going from solid to liquid. Once all of my material becomes a liquid, I start to see a temperature change again. That's section 3. As long as it's all liquid, we can have a temperature change. If we have a temperature change, we can calculate the energy as Q equals mc delta T. But this time it's the specific heat of the liquid. different phases have different specific heats. Ice has a specific heat that's different from water. Water has a specific heat that's different from steam. All materials have different specific heats based on phase. Okay? Liquid, 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 then it starts to change phase again. We go from liquid to gas. What's that called? Evaporation or boiling. We reach the boiling point and it flatlines again. As long as it's boiling, the temperature doesn't change. Because now my energy can't go into changing the temperature. My energy is going into overcoming intermolecular forces and pulling those liquid particles, molecules apart, making them spread out into a gas. In section 4, to calculate the energy added, it's the enthalpy of vaporization times the number of moles. And then finally, once we've gone completely from liquid to gas, we have gas. It changes temperature all the way up to whatever my assigned final temperature is. And we have Q equals MC for vapor delta T. Or C for gas, either one. If I added all these up, I could find the amount of energy it took to go from the solid at the initial temperature to the gas at the final temperature. But I have to go through all of the phases individually because you have some phase changes happening. You don't have the same C the whole time, specific heat changes throughout the process. All kinds of things happen. Questions about that? Okay, let me erase and then we'll move on. The opposite of a heating curve is a cooling curve. Here, we're starting at some high initial temperature with a gas, going down, turning to liquid. This would be the boiling point again, going down. This is the melting point, turning to solid, and then freezing and getting to the final temperature. Same math, but this time you're going to wind up with negative values. Energy is being removed from the system. Energy goes in for a heating curve, energy comes out for a cooling curve. Math is the same, you just wind up with negative values. Questions about that? Okay, we're going to do an example. Do you all want me to give you a second? All right, so here's some data. It gives us the specific heat capacity of ice, water, and steam. It tells us the molar heat of fusion for water, got delta H of fusion, the molar heat of vaporization for water, and then the melting and boiling points. Part A, how much energy is released when 1 mole or 18 grams of water at 20 degrees Celsius is frozen and then cooled to a temperature of -2 degrees Celsius? So we're starting with water at 20 and going to ice at -2. So we have to start and we have to change the temperature of our water. Part 1, Q equals mass of the water, C for the water, temperature change of the water. Right? Water at 20 to water at 0. Then water at 0 starts to freeze. And I have to find the energy it takes to freeze it. Once it's frozen, I can change the temperature of my ice from 0 to -2. 3 parts. Change the temperature of the water, freeze the water, change the temperature of the ice. Okay, so we can plug in numbers here. Q equals, the mass is 1 mole or 18 grams. C for water is 4.18 joules per gram Kelvin. And the temperature change, we're going from 20 to 0, so the final temperature is 0. So my temperature change is -20. And I get -1,505 joules for part 1. Negative because energy has to be released for the temperature to go down. Part 2, Q equals delta H of fusion, molar heat of fusion, is 6.02 kilojoules per mole, or 6,020 joules per mole, times 1 mole, gives me 6,020 joules. But we have to be careful here. When water is being frozen, when anything's being solidified, energy has to be released. Vice versa, if it's being melted, energy has to be absorbed, and that would be positive. You're never going to be told that. That will never come out in the math. You just have to know that. Part 3. Q equals, the mass is the same. We still have 18 grams of stuff. The specific heat of ice is 2.05. And we're going from 0 to -2. So my temperature change is -2 Kelvin. And I wind up with -74 joules. There's somebody at the door. Oh, hold on. Yeah, go ahead.
Sorry,
You're fine. Yes, it's very warm.
Graceful. Oh, great.
Okay, I'm going to go ahead and finish. To find the total energy for this to happen, to go from water at 20 to ice at -2, you just add up these 3 values. So -1505 plus -6020 plus -74 gives me -7600 joules. That would be the answer to A, the energy released. So 2 options here. You can say -7600 joules, or you can say 7600 joules of energy released. Those are synonyms. This means released. If you say -7600 joules released, that's like a double negative. You can't say both. 7600 joules released, or just -7600 joules. Part B. Considering only the energy released in the phase change above, what would be the temperature rise observed in a heat bath made of gold with a mass of 0.502 kilograms? The specific heat capacity of gold is 0.129 joules per gram Kelvin. So here, this is our energy. So Q equals MC delta T. 6,020 joules goes into the gold bath. The mass is 0.502 kilograms or 502 grams. The specific heat is very low, 0.129 joules per gram Kelvin. And we're finding delta T. The gold bath would go up 93 degrees Kelvin. 93 Kelvin. That's a big temperature change. It's so large because gold has such a low specific heat. Okay, any questions?